In this video, we're going to answer the question, what does I raised to the I power equal? Where I is the imaginary unit, square root of -1. Well, I'll quickly solve this, and then we'll do a little bit of a review of complex numbers and then discuss the general case where we take a complex number base raised to a complex number exponent. So on this one, what do? Well, the first thing is express the base I in exponential form. So we can write I, the square root of -1 is I, and we can express it in polar or exponential form as e to the I pi over 2. And then we add to this, to make it multi-valued, 2 pi n, where n is an integer. As long as we add integral multiples of 2 pi to the angle, we get back to the same spot. So I has an infinite number of representations where n are integers, 0, plus minus 1, plus minus 2, and so on. Now, for I, we represent it on the exponent in rectangular form, which is the form that it's in. I is 0 real part plus 1 imaginary part. So we now take I raised to the I power is e to the I pi over 2 plus 2 pi n, and then this is raised to the I power. Well, using properties of exponents, this now becomes e to the I squared times pi over 2 plus 2 pi n. And I squared, remember, right, I squared is -1. Because I is the square root of -1, I squared is the square of the square root of -1, which is just -1. So this now becomes e to the minus pi over 2 plus 2 pi n. We can now represent this by taking the negative power and putting this in the denominator. So this becomes, we'll first split it up as e to the minus pi over 2 times e to the minus 2 pi n, using the properties of exponents. So this now becomes 1 over e to the pi over 2 times 1 over e to the 2 pi, and I'm going to represent it this way, raised to the n power. Well, that's the result, as n can be 0, 1, plus minus 1, plus minus 2, and so on, any integer. If n is 0, this becomes 1, and the principal value of I raised to the I power is just 1 over e to the 2 pi, and or pi over 2, and we can express this as a real number. So this is 0.2078 and it goes on forever. It's an irrational number. And this part here is 1 over 535.491, and so on. It's also irrational, and that's raised to the n power. So as we choose different integer values for n, we get different values for I raised to the I power. The principal value, of course, is when n is 0. So the principal value is 0.2078, and so on. When n is equal to 1, the value is 3.8 8, 2 times 10 to the minus 4th. This is for n equals 1. This is n equals 0. For n equals 2, the value is 7.25 times 10 to the minus 7. And when n is minus 1, this just flips up and we have 535 times 0.2. And the value is 111.317. When n is minus 2, the value is 59,609.7, and so on. So we can get an infinite number of values for I raised to the I power. But what's really curious about this is we have an imaginary number raised to an imaginary power, and the values that it represents are all real. So I raised to the I power is a real number, and its principal value is 0.2078. Now we'll do a review of complex numbers and look at what z1 raised to the z2 power, where z1 is a complex number, x1 plus I, y1, and z2 is x2 plus I, y2. We'll see how to compute that particular value here of a complex number raised to a complex number. Now we've arrived to the point where we can extend exponentiation to powers that are complex. We're going to take a complex number base to a complex power. So we'll start off here. We have z1 and z2 are elements of the complex number. They belong to the complex numbers. So what is z1 raised to the z2 power? Now, what we'll first look at is we're going to put the base z1 in polar form and the exponent in rectangular form. That's the way we need to proceed here. So z1 is going to be m1 e to the I theta 1 plus 2 pi n. We're allowing multiple values for the complex numbers so we don't run into trouble with our properties of exponents. Then z2 will be x2 plus I y2. So z1 raised to the z2 power is m1 e to the I theta 1 plus 2 pi n raised to the x2 plus I y2 power. Now we'll expand this out by the taking the sums of the exponents. Remember, we can have a property where we have b raised to the r plus s power. This is b to the r times b to the s. So that's what I have. That's what we're going to do here. So we have m1 e to the I theta 1 plus 2 pi n to the x2 power times our base again, e to the I theta 1 plus 2 pi n raised to the I y2 power, just using this property here on the exponent. Now this, we'll work on this now. We'll use the property that b to the r raised to the s is brs. If we take a base and raise it to a power and then raise that to a power, it's the same as taking the base to the products of the power. So we first Also, one other property we're going to use here is if we have our b1, b2 raised, say, to the s power. This is b1 to the s times b2 to the s. That's what we're going to do here first. This is our b1, this is our b2, so we just move our exponent on through. So this becomes m1 to the x2 power times e to the I x2 theta 1 plus 2 pi n. What I did here is two things. I first split using this property, and then using this property here, e to the r raised to the s is e to the r s, using this property. So now this becomes m1 to the x2 e, bringing the x2, combining it with the exponent on e, we have that. Now we work on this one. Same thing. m1 now is raised to the iy2 times e. The iy2 comes down here, so we have I squared y2. I squared is minus 1, so this becomes minus y2 theta 1 plus 2 pi n. Now, everything makes sense here except for this factor here. We have to work on that a little bit. m1 raised to the iy2 can be written this way. We'll write m1 as e to the natural log of m1. That's our m1. E to log m1 just gives us m1, and we're raising that to the iy2. Now, we have e to the power raised to a power, so we can use this property. We just combine the exponents. So this becomes e to the iy2 natural log of m1. And it has a magnitude of 1, as we can see here. So now we can put this in here and combine. So we end up now with m1 x2 e to the minus y2. I'm bringing this over. Okay, we have that written, and now I'm going to work on bringing this minus y2 theta 1 plus 2 pi n. So we've got that in there. And then we're going to multiply. We have this, which is e to the I. We have x2 theta 1 plus 2 pi n. And we also have this for m raised to the iy2, so we can add that in. This becomes y2 natural log of m1. So this is the expansion of z1 raised to the z2. It's fairly complicated, but we can rewrite this in this fashion, where what I'm going to do is separate out the exponents that have n, which changes, and express factors that change, and those that are fixed. So we can rewrite this as m1 x2 e to the minus y2 theta 1 from here times e to the I. Now we have an x2 theta 1 plus we have y2 natural log of m1, and then we have a minus y2 2 pi n, so this becomes minus 2 pi y2 n from this term, and then we have an x2 times 2 pi n, so e to the I 2 pi x2n. Now this part is fixed. It does not depend on n. This would be the principal value, and this is variable. This is a function of n. When n is 0, we get the principal value. The exponent here becomes 0 when n is 0. The exponent here becomes 0 when n is 0. So e to the 0 times e to the 0 is just 1. So this drops out when you're just looking at principal values. This is the principal value of z raised to the z, or z1 raised to the z2 power. Now we can also represent this yet in another form using a trigonometric form. And we get there by using the exponential form and just easily converting by using Euler's identity. Remember, Euler's identity is e to the I pi, or let's say e to the I phi is cosine phi plus I sine phi. We'll use that to expand this out. So I'm just going to use, start with this form here. And what we will do is this remains, this is the magnitude, and then this is the angle. So the magnitude then, z1 raised to the z2 power, is m1 to the x2 power e to the minus y2 theta 1 times plus 2 pi n. Okay, that's our magnitude. Now we're going to apply Euler's identity to this. So we have now the cosine of x2 theta 1 plus 2 pi n. That's oops. Yeah, it's kind of sloppy. I'll redo that. I'll write this as the cosine of x2 times theta 1 plus 2 pi n plus y2 natural log of m1 plus I times the sine of this very same angle here, x2 theta 1 plus 2 pi n plus y2 natural log of m1. So that's in trigonometric form. That's the expansion of z1 raised to the z2 power. Now we can express z1 raised to the z2 power again as its principal values by just making n equal to 0. So principal value z1 to the z2 will then be m1 x2 e to the minus y2 theta 1. The n is 0 to get the principal value, n equals 0. And then this is times the cosine of x2 theta 1 plus y2 natural log m1 plus I sine x2 theta 1 plus y2 natural log m1. So that's the principal value there for z1 raised to the z2 power. Here's our expansion that we just derived. I have it partitioned into the fixed part and the variable part, as n is an integer that can go, n can be 0, plus minus 1, plus minus 2, and so on. Be a member of the integers. When n is equal to 0, we get the principal value of z1 raised to the z2 power. When n is 0, the exponents become 0, e to the 0 power is 1, so this just drops out. So this part is the principal value here when n is equal to 0. Let's go to the original problem that we started with, I raised to the I power. Remember that we derived at the beginning that this was e to the minus pi over 2 times e to the minus 2 pi n. Let's go ahead and use our expansion to check that out. Now, I raised to the I power, so both z1 and z2 is I. Well, with z1 we express I as an exponential form, so in this case I becomes e to the I pi over 2. This is our z1. Our z2 is expressed in rectangular form, and z2 is I, which is 0 plus 1 times I. Now, this is 1 time, the magnitude of I is 1, so this becomes 1 times e to the pi over I to the pi over 2. Now, our m1 then is equal to 1. Our theta 1 is pi over 2. And for z2, our x2 is 0, and our y2 is equal to 1. Now let's put it in. So we have I raised to the I power is m1, which is 1, to the x2 power, which is 0, times e to the minus y2, which is 1, times theta 1, which is pi over 2, times e to the I, x2 is 0, times theta 1, pi over 2 is 0, times pi over 2 is 0, so 0 times pi over 2 here, plus y2, which is 1, times the natural log of m1, which is 1, times e to minus 2 pi, y2 is 1, and n, and then we have e to the I 2 pi, x2 is 0, times n. Well, let's simplify this. 0 to the 1 is 0, so this becomes e to the minus pi over 2 times natural log of 1 is 0. 0 times pi over 2 is 0, so this is e to the 0, or 1. And then we have e to the minus 2 pi n from here, and the exponent here is multiplied by 0, so it's e to the 0, which is 1. So here's our value. And It agrees with what we started out with. So the formula does reduce down to give us exactly what we had before. Let's now use our expansion for the complex number raised to a complex power for finding the value of some complex numbers raised to a complex power. Suppose we have x is equal to the a plus I. What's this equal to? Well, the first thing we do is we need to express the base in exponential form and the power in rectangular form. So the base, x, is our z1. This can be written as x times e to the I0. We just use the principal value for the base because we took care of the multiplicity of values by adding 2 pi n in our derivation. So in this case then, our m1, the magnitude is x, and the theta 1 is 0. This is I0. We'll just call that 0. All right. Now, our z2 is a plus I, which is 1 times I. So our z, or our x2, putting this in terms of rectangular form, our x2 is the real part, which is a, and our y2 is the imaginary part, which is 1. So now we put in our values. X to the a plus I then becomes m1 to the x2 power. m1 is x to the x2 power is a, times e to the minus y2, which is 1, times theta 1, which is 0, times e to the I. x2 is a, times theta 1 is 0, plus y2, which is 1 times the natural log of m1, which is x, times e to the minus 2 pi. y2 is 1 times n, and the last factor, e to the I, 2 pi, x2 is a, and then times n. We can simplify. E to the minus 1 times 0 is e to the 0, so this just becomes 1. A times 0 is 0. And we can now combine. So we have x to the a times e to the I, natural log of x, times e to the minus 2 pi n, times e to the I 2 pi a n. Now I'm going to combine these two. This is of the form the same base. This is like b to the s times b to the r. So this is b to the s plus r. So I just combine exponents. This will be x to the a. This is also part of the magnitude, e to the minus 2 pi n, times e to the I. We have natural log of x plus 2 pi a n. So that's our form for x to the a plus I. We could bring this into the denominator and write it as x to the a over e to the 2 pi n. And then we can write this out using Euler's formula in trigonometric form if we want to. So this would become the cosine of natural log of x plus 2 pi a n plus I times the sine of natural log of x plus 2 pi an. Now, when a is equal to 0, let's look at what happens when we have x to the I. This is when a is equal to 0. So when a is 0, we have x to the 0, which is 1. So we end up with 1 over e to the 2 pi n times a is 0. So this drops out and that drops out, and this simplifies to the cosine of the natural log of x plus I times the sine of the natural log of x. Now, when n is equal to 0, we get the principal value. So the principal value of x to the I will just, when n is 0, we get e to the 0, so that becomes 1. So it's just the cosine of the natural log of x plus I times the sine of the natural log of x. So that's the base value. Here is the general form of x to the a plus I that we just derived, and we're just going to now substitute in a equals to 1 to get x to the 1 plus I. Doing so, a is equal to 1, so we end up with x over 2 pi n times the cosine of the natural log of x plus 2 pi n plus I times the sine natural log of x plus 2 pi n. A is equal to 1 in that case. Now the principal value is when n is equal to 0. So when n equals 0, x to the 1 plus I is equal to, or I'm sorry, this is e raised to the power. So when n is equal to 0, e to the 0 is 1. So we just end up with x times, and n is 0, this drops out and that drops out. So we have the cosine, the natural log of x, plus I times the sine of the natural log of x. So it's an interesting form. X raised to the 1 plus I power, the principal value, involves sines and cosines. Now we can make use of that, interestingly enough, is if what happens if we have x to the I. Let's look at x to the I. And that is x to the a plus I evaluated when a equals 0. So when a is 0, we get 1 in the numerator, and these drop out, and we can immediately write that it is 1 over e to the 2 pi n times the cosine of the natural log of x plus I times the sine of the natural log of x, because a becomes 0. Now the principal value on this is when n is equal to 0, so we can write x to the I, its principal value, as the cosine of the natural log of x plus I times the sine of the natural log of x, because when n is 0, e to the 0 becomes 1. So here's the principal value of x raised to the I power. And the principal value we have of x to the 1 plus I is this. Well, we can see that these are related in that if we integrate x to the I, we raise the exponent by 1 and divide by the exponent. So this is, in a sense, related to the integral of this form. So let's look at the integral of x to the I dx. The indefinite integral. This becomes x to the I plus 1 over I plus 1. So this differs from this just by I plus 1 in the denominator. Let's rationalize this by multiplying by the conjugate. So we have 1 minus I times x to the I plus 1. And then we multiply the denominator by the conjugate, we get 2. I plus 1 times I minus 1 is 2, because we get 1 times 1 times minus I times I, which is a plus 1, and the cross terms drop out. So, what we have here then is putting in for here, for our I, x to the I plus 1, we can write this as 1 minus I times x times the cosine of the natural log of x plus I times the sine of the natural log of x. What I've done is I substituted in for x to the I plus 1 this trigonometric form, and then this is divided by 2. Now, we have the product of two complex numbers, so we can expand this out, and this becomes x over 2 times the cosine of the natural log of x plus the sine of the natural log of x plus I times the sine of the natural log of x minus the cosine of the natural log of x. I'll let you expand that out. That's just, we multiply 1 minus I times this complex number, and that's what we'll end up with. Now, we can equate imaginary and real parts. If we look at this, again, remember this, we take the integral, we're integrating x to the I with respect to x, so if we integrate this with respect to x, we're integrating this portion with respect to x. So this is going to be equal to this. We just determined that. So we equate imaginary and real parts. So the real part is the integral of the cosine of the natural log of x with respect to x, and that's going to be equal to this portion. Now let me write this out a little bit. Get rid of some of this. Don't need that. Okay, so we have the integral of x to the I dx, which we have here is the integral of the cosine of the natural log of x with respect to x plus I times the integral of the sine of the natural log of x with respect to x. And that's what we have here, and that's equal to this portion. So we can say here is the real part, here is the imaginary part. X over 2 times this is the real part, and then x over 2 times that is the imaginary part. So we can write that the integral of the cosine of the natural log of x with respect to x, that's the real part, is equal to this, which is x over 2 times the cosine of the natural log of x plus the sine of the natural log of x, and equating the imaginary part, the integral of sine natural log of x dx will be equal to x over 2 times the sine of the natural log of x minus the cosine of the natural log of x. So we have two integrals for the price of one because we're dealing in a complex plane. And that's the power of complex numbers. When you do operation on a complex number in general, the operations act independently on the real and the imaginary parts, and by equating imaginary and real parts on two sides of the equation, you get two different relationships. Now, one last thing is we'll just do a couple real quick ones to wrap it up. How about 2, the number 2, raised to the I power? Well, we know that we can express 2 as e to the natural log of 2, and that's raised to the I power. And using properties of exponents, this becomes e to the I natural log of 2, and we can write it out in trigonometric form. This becomes the cosine of the natural log of 2 plus I times the sine of the natural log of 2. So that's the value of 2 raised to the I power. How about what is the cosine of 2 plus I sine of 2 raised to the pi power? Well, make note, we can write this out as, let's put it in exponential form. So in exponential form, the magnitude of this, the magnitude squared is just cosine squared of 2 plus sine squared of 2, which is 1. Using trigonometric identity, the sine squared plus cosine squared of the same angle is identically equal to 1. So our magnitude is 1. And then what is the angle? Well, the angle is theta, which is the angle whose tangent is the imaginary part, which is sine of 2 over the real part, the cosine of 2. Well, what's sine over cosine? That's tangent. So what we have here is the arctangent of the tangent of 2, which is 2. So writing this, we have magnitude, which is 1 times e to the I 2. The angle is 2. So that's this portion here in the brackets, and then we're going to raise that to the pi power. So this becomes e to the I 2 pi. Well, we recognize that as being identically equal to 1.0. So it's interesting that cosine of 2 plus I sine of 2 raised to the pi power is just equal to 1. How about something like e to the I power? We know that this is e to the I times 1, so this is the cosine of 1 plus I times the sine of 1. Well, the cosine of 1 is 0.5403, and the sine of 1 is 0.84147. So e raised to the I power has this value, and e to the 2 pi I we know is 1. But we can rewrite this using properties of exponents. E to the 2 pi I can be written as e to the 2 pi raised to the I power. Well, e to the 2 pi from before is 535.4916, so on, raised to the I power. So this number is equal also to 1. 535.4916 raised to the I power is 1. So that wraps it up. Here is our general form for the expansion of a complex number raised to a complex number.